I believe I sent you an email on stereochemistry for you to print on your own. Okay? We'll get there in about a week and a half, 2 weeks, but you can have that now if you're looking ahead. Okay? Reading about stereochemistry. I'll get you other handouts. We have a thermodynamics handout we need to finish up. I also sent you Intro to Alkenes. Mine is blue. Okay? That has your nomenclature. Nomenclature is a different video. Okay? I do all nomenclature by video, almost all. Including with the alkene nomenclature is the important idea of stereogenic alkenes. Using cis or trans, we know that, but also E and Z terminology. Very important. Physical properties. We can finish up this handout. I'm sorry. We don't have that one yet. Intro to alkenes. We will have to look at physical properties there. A couple other things in the back of that. Kind of miscellaneous. You all have that one printed yet?
Yes.
What I sent you? Yeah? Everybody have that one printed?
Not everybody.
Okay. Please have that one printed by Monday. Remember what I said in the email. I may not have mentioned that one, but we do need to look at a little bit of that in class. The other one, you have another good week to week and a half. Okay, 2 handouts today. The green is an outline. The white is sort of the workings of the material. Document camera. Lab today, recrystallization. Yesterday, a little bit long. We turned a 30 to 45 minute procedure into 2.5 hours. Okay? It's because I gave you the entire lab. Maybe I should only give you an hour to do this lab. Then maybe you would do it more time efficient. Okay? Maybe this afternoon we can work a little quicker. I know it's your first time, and I did not tell you this, but as you move forward, you're going to have to recrystallize in like 30 minutes. Okay? So you work on being more efficient in lab. It's also the benefit of Friday lab. The second lab, I kind of push you to do things differently after I see Thursday. I can't remember it every year. The next day, I always remind you, hey, this happened yesterday. So today we need to work a little bit more efficiently. Okay? The lab, get it done. But also understanding, you guys may not know. Maybe this should take 2 hours. I'm just basically telling you it should not take 2 hours. Okay. An hour should be plenty. We don't want to work, frantically or too fast. But understand that I see a good bit of kind of standing around and just kind of waiting too long. Okay. So you need to hit your marks, get things done, come prepared. When you come to class, when you come to lab, that's when the curtain is pulled back and you're on stage and you're good to go. Dress rehearsal comes before lab, before class. All right? Any questions before we get going? Lab report, did we say Monday for unknown lab? Still good with that? Okay, I'll return the other lab reports this afternoon. And I said a few things about that. Again, please make sure you read the requirements for lab reports. All right? Okay, alkene reactions. There's a warm-up page there. There's outline on the second page. But back of the first, please also read the finishing on the lab safety page. I think there's a section about finishing the lab each day. Finishing for the day or finishing up. These are requirements that before you leave the lab you need to do. Okay? Many of you are not doing that. Thank you to those who are consciously following those guidelines and making sure that you do those things. Those who are not, please read again and please understand that that's a requirement. Expectation. Okay? Okay, this is a summary here, this page here. Reactions. Please read my headings. My headings are meant to be very informative, strategic, to tell you what you're doing. Okay? What type of reactions are these? Summary of what type of reactions? Okay, do you think that term's important? Yeah, it's very important. We need to understand what we're doing before we then start doing it. So terminology is very important. Okay? Roman numeral 1 and 2, the first type of reactions will be with H+. Bl acid. As the electrophile. What is an electrophile? Okay, need to make sure you know what it is. Carbocation intermediate. All right. Number 2, do these involve a carbocation intermediate? And there they do not. All right. That right there is hugely important. Okay. Orienting yourself. What's going on? Understanding headings. We don't just. I fear that sometimes you guys just read a heading, and then it just kind of goes in and out. All right. The headings, the titles are meant to be very informative. Do not move on until you understand what is stated. At least for my handouts. And the way I want you to learn the material and the way I present the material. All right, the first reaction will be reaction of an alkene. This is just a cyclic alkene. Does not have to be cyclic. Site of reactivity. We've got H+. We said we'd have that each case. But then we're going to have a different nucleophile. This is just HX. We'll make what type of compound? Alkyl halide. We'll make alcohols, ethers. We can convert an alkene to various types of functional groups. Converting one functional group to another is a big part of organic chemistry. Reactions down below. Okay? Again, looks pretty daunting. But we've got to find the commonalities to make it much easier. One step at a time, one day at a time. Here's our outline. A. Now this A may not be the same as the other A. I'm not sure, but the heading should be the same. It may actually be Roman numeral 1 over there. They kind of separate. We'll begin with electrophilic additions involving carbocation intermediate. The electrophile is going to be H+ or C+. Roman numeral 1, addition of HX to give alkyl halides. Also known as what? Hydrohalogenation. So that Roman numeral 1 is the same as, well, that's here. Okay? Looking at this reaction right here first, alkyl halides. Okay. Mechanisms. This page here and maybe just one page. Well, it's one handwritten page and then it's 2 typed pages. Well, really 3. The rest of the handout, from here to the end of the handout. Perhaps one of the most important handouts I'll give you in Organic 1. Or 2, right there. Okay? Hugely important to understand this material. Mechanisms, we get acid-base mechanism. All right? And in the reports I'm seeing, need to work on the mechanisms because the arrow needs to mean something very precise. Right? I'm seeing a lot of incorrect arrow usage. Need to work on that. We only had one mechanism for acid-base. I gave you that. You need to review it. Understand the arrow movement. Now we're going to advance to beyond acid-base mechanisms, alkene mechanisms. And really, this page, it's more than alkenes. This is the mechanisms you need to know for all of organic chemistry, including the rest of Organic 1. Right here. Not all of it, but the introduction and a lot of the foundation. 2 mechanisms for making nucleophile to carbon bonds. Okay? Please read this. All right, I'm not going to read it to you. After you go through it, we'll see if there's any questions about it. Hugely important. And then I give you some free information. Okay? Guidelines, free information, what not to do. tremendously important. In the end, this stuff is not overly difficult. Okay? The problem will be you get behind and you don't take my advice and understand that the few pages I gave you are critical to understanding. Okay? So I would get a cup of coffee or whatever and sit down and spend time on those pages and say, if I'm going to succeed in organic chemistry, I must understand this right here. Because that's what Dr. Stevens told me. All right? So, addition of HX to give alkyl halides. Let's look at the mechanism, including rate determining step. Let's draw a reaction according to diagram. Let's look at things like Regio Selectivity. All right? Okay. I'm trying to get your attention because I want you to succeed. And right now, we're going to step it up a gear, okay? And I don't want you to get behind. I don't want you to not succeed. I want you to do as well as you want to do. All right? Did we finish up thermodynamics handout? Okay. I'll send out an answer key to some of those problems. Like that there. All right. I'll send out an answer key today. Did we go over, did we mention the very last one? The last reaction according to diagram? I don't think we did. How many intermediates in this reaction? Going from, this looks like AB reacting with C to give BC. How many intermediates? How many intermediates in this reaction? 0, right? Okay. I heard a few people say 1. No, it's 0. Okay. We mentioned above what an intermediate looks like. Okay. On the previous page. All right. Just a transition state. And here we go. Any questions about that handout before we move on? Okay, addition of HX to alkene. Here we go. A while back, this was written on the board. Okay, a lot of material to write on the board, and end up just doing a lot of writing, and it slows us down. Okay, so now this is on a handout here. Still need to do some note taking to make it your own and make it informative for you. Yeah. Okay, addition of HX, hydrohalogenation. If we take an alkene, okay, certain formula, we can react it with what? HX. X being halogen, in this case Br minus, or Br. HBr. HBr can be shown covalently or it can be shown ionic, depending on the conditions. And we get a reaction in which the HBr has added to the alkene. Because if you look at formula, the formula now has HBr added to it. Right? And so we call this an addition reaction. As simple as that. And we're adding HX, HBr an example. Okay? And we say we have hydrohalogenated the alkene. What type of compound did we make? An alkyl halide, right?
Alkyl halide?
It's alkyl halide. Specifically, it's an alkyl bromide. Okay? Yeah. Common way to make alkyl halides right here from alkenes. Mechanism for this reaction. The pi bond is a source of reactivity. The electrons are not held that tight. Pi bond is weaker than sigma bond. It will react. Okay? These electrons, now HBr is polarized. Okay, so the H is partial positive. These are electrons. They're inherently negative, and they will be attracted to the H. We can show this mechanism either with this covalent, or you can just go ahead and show it ionic. And you don't need a mechanism to show it ionic. I'll allow you, and we can just start with like that if you'd like. Of course, because we know HBr can be ionic. And down the road, we may have a reagent that cannot be ionic, then you'd have to show it covalent, which is polarized, polar covalent. In any event, the H has got some positive character. And so it's attracted to electrons. That makes sense, right? Something positive. If there are electrons around, they'll be attracted to it. The H plus here is called the electrophile. Okay? In this mechanism, these electrons move and make a bond to the H. And how do they move? Before we had a lone pair. You know, maybe an amine with a lone pair, and we did something like this. The lone pair may be attacked at H. Well, here it's the pi bond attacking the H. Okay? And the way this is sometimes shown is, well, I'll do it with sort of my arms here. The electron double bond is sitting here. Okay? The pi bond breaks away from the carbon and goes and just makes a bond to H. All right? Now, physically, how is this happening? We could show it maybe a little bit different physically, but mechanistically on our page, we show it as just swinging out. So these electrons just swing out and make bond to H, but these have to leave and they move on to Br. That Br wants the electrons anyway. Okay? Now, the Br is pulling on these electrons. When these attack, it's kicked off. Okay? What does that give? And you can do it either way. You can do it here. What does arrow mean? Okay, every time we do an arrow, we need to know what does arrow mean. We also start when we move an arrow by saying these electrons. These pi electrons move and make bond to H. These electrons move on to Br. What does that give? It should give this. Right? This moves and makes bond to H. There's the bond we just made. But when it left the carbon over there now only has 3 bonds. And lo and behold, that's a carbocation. Carbon is a positive. All right? But what do we create right here when the electrons moved on to Br? We created the Br minus as a sole atom entity, and it took on the 4th lone pair. Where'd the lone pair come from? Right here. Electrons moved on to Br. And lo and behold, that's minus. That's bromide. So this first elementary step here gives a carbocation intermediate plus Br minus. The next step is the Br minus, these electrons, then go and make bond to the plus. That's just physics. Minus likes plus. And this means that that's making a bond to the carbon. There's that bond. And we're done. There's your product. How many steps in this overall mechanism?
2.
3. It's 2 steps. Reacting with alkene to make the carbocation, and then reacting of the Br minus with the carbocation to get a final product. 2 steps, yeah? Who said 3? Why did you say 3?
Why 3? Because first sigma bond to the H, then the electrons move to the Br.
This is all concerted.
So,
That's concerted. That means those 2 processes are happening at the same time. Because we would never just make bond to H, because the H would then have 2 bonds. Not going to do that. Right? To make a bond to H, something has to leave or break. 2 steps. This comments over here. Of course, arrows show movement of electrons, not atoms, right? H plus is the electrophile. What does electrophile mean? What's a winophile?
something that likes electrons.
One like wine,
Something like
right? What is an electrophile?
something that likes electrons.
Something likes electrons. Will H plus like electrons? Yes. Okay, electrophiles tend to be positive things. either partial positive or a full positive. Br minus is called the nucleophile. What is it like?
Proton level.
Like the nucleus. That's a little bit not direct. What is the charge of a nucleus?
Positive.
Positive. Okay? So more specifically, this could be called a positive phile. Would a Br minus like positive charges? That's physics. Minus likes positive. Okay? So we call that's the terminology. Okay, for different things, how they react. And guess what? The electrophiles react with nucleophiles. Because one likes positive and one likes negative. It's just simple terminology. Two-step mechanism. With what type of intermediate? The intermediate is mainly going to be focusing on the organic molecule. Carbocation intermediate, right? And you've got the green A, yeah, top. Electrophilic conditions involving carbocation intermediate, yeah. The electrophile is H plus. Mechanism, including rate determining step. Which one's the rate determining step? Which step do you think would be? Maybe we should draw RC diagram. Let's see, reaction-supported diagram. We have some type of energy, reaction progress. Okay. Label the alkene as A. All right. One intermediate in this reaction, carbocation energy compared to A. It'll be higher because it's a charged, hot, formal charge. It'll be higher in energy. Okay. So put it up here. Label that as B. And final product, how does it compare to A and B?
Lower.
Back down. How does we'll call that C, A, B, and C. How does the alkene compare to the alkyl bromide? Which is more stable? You can pull out your calculator and do calculations with bond strength tables. Well, we can also just assess that. And we'll do this in the other handout, the one you need to print for Monday. Okay? Alkene or alkyl bromide, which is more stable?
Alkyl bromide.
Why?
Do the single bonds, are they more stable than the pi bond?
Yes. Look what we did. We went from a pi bond was broken. What was formed over here? 2 sigma bonds. Okay? We formed that one. Where was the other one we formed?
To the hydrogen.
Right. Everybody, there's a new H here, right? On the end? You got to know where H's are at. How did that new H get on the end? Right here. N carbon went bonded to H. Right? How many H's there? 2. How many H's there? If we get rid of it, how many are there?
3.
3. That's now a methyl. CH3. Okay. You got to know where H's are at. It's a common problem to lose track of H's, and thus that leads to other problems. All right. So actually, yes, the product is lower. So let's draw it a little bit lower. All right. When we do this, do we just go straight there? Or do we do something more like that? Or like that, right? Okay. We looked at reaction-coordinate diagrams, transition state. Question?
Would the activation contributor go up to B instead of going high? Or
What do you mean? This is the activation energy here?
yeah, like wouldn't it just go up to B? Like why is there a hump before you get to intermediate?
Why is there a hump before it gets to B?
No,
Well-
I got it.
I mean, we looked at this last time. Right here. Here's intermediate. There's a hump before you get to intermediate.
I
Yeah.
was thinking about transition state like that.
Okay. But let me pick on you a little bit. Okay. This here was to prepare us for moving ahead. So we need to understand all this. Everybody came understanding these reaction coordinate diagrams? And after you looked at it, you then said, okay, what am I missing here? All right. Where are we at? Right there. We don't need to move right there. So there we go. Now, that's the transition state activation energy leading to the carbocation. Now we got to get the final step, the BR text. What type of activation energy for that?
A little hump.
Little hump. Why a little hump? That's because we're falling downhill. See, I could have made this even bigger here. This is all just however, it's all relative. That's clearly higher than this. Falling downhill doesn't take much activation energy. And yes, we will draw it right here. Because for a given step, that is the activation energy for that given elementary step. Falling downhill doesn't take much energy. If you don't believe me, go to the top of the stairs on the 3rd floor. Okay? You can do this both. You can go to the bottom. Go to the bottom and just do like this. You ain't going to go up. But go to the top and do like this. You're going to go down pretty quickly and pretty easily. Falling downhill, it doesn't take much activation energy. That's a general statement to help us understand that. So, which is going to be the fastest or the slowest step?
First one.
First one. The first is your rate determining step. The next one is fast. Forming the carbocation is typically rate determining step in all these reactions. Nucleophile then coming in is a fast. Boom, that's fast. Yeah? Okay, so we can answer questions about this reaction coordinate diagram. We could draw one. But again, all that was introduced in the previous handout. As an example. Is this reaction thermodynamically favored?
Yes.
Yes, that's just looking at this. C is more stable than A. That's thermodynamics. Okay? Delta H or delta G, it depends on what you want to put over here. I would stick with delta H because that we can more easily quantify. Okay? And when we looked at the bond strengths, that's what I was looking at, delta H, yeah? Yeah. Is this reaction favored by entropy?
No.
What is entropy? What's going on there with this? How do you assess that? 2 molecules going to 1. Alkene HBr reacting to form 1 alkyl bromide. 2 to 1, that's not favored by entropy, is it? No. So is the reaction overall favored in terms of overall delta G? A little bit harder to assess because you got 2 conflicting terms. Favored by thermodynamics, not favored by entropy. We're not going to go any further than that. We could ask this, would you want to heat this reaction to make it faster? And would heating this reaction help it? It depends. You may have to heat it enough to get it to happen, but would further heating be warranted and good? No. Entropy is bad. Temperature magnifies entropy. You don't want to magnify a bad term, right? Okay, so those are the things we need to understand. Regio selectivity. Why did we not react to give this alkyl bromide? Note that the one we got, the bromine was on which carbon? You have any terminology for that carbon?
Tertiary.
Yes. Why does it end up on tertiary carbon? Yes. It does not end up the other way. See, down here, we added the H here and there. H here, okay. BR thumb, H pointy finger. Above, we did it the other way. BR here, H over there. That's called regio selectivity because the bromine is bonded to different regions. The tertiary carbon would be called a region. This could also be called site selective. But we say regio selective. Why not here? this is also A. ABC, let's call this E, and D will be our intermediate here. To get this, that means that I'll use this ionically, that means the electrons swim this way. Okay, grab them over here and pull them away from that carbon and do this, and that would give H here, yeah, and carbocation here. Right? Here we go. Grab my hand and pull it. There's an H over here. Grab it. Everybody grab it. Pull it over there to make bond to H. There's that bond to H. And when it went over there, it left this carbon without a bond. It's now positive. Okay? A, B, C, A, B, C. Let's call this D. From D, then we can go to E. How do we go from D to E? BR attacks here. We're not going to show that. Let's compare B to D. Which is more stable? B, you noted up there. Which carbocation is more stable?
B.
That's a tertiary carbocation, and this is a primary. This has one rich friend stabilized in it. sp3 carbon donates to stabilize. How many rich friends did we have up here?
3.
3. Tertiary cation more stable. Carbocation stability. Tertiary is better than secondary, better than primary. And that's better than just plain methyl, because that's not even primary. Why? Inductive effects, right? Inductive donation of the sp3 carbon. You have more in the tertiary. So if we put D here, where would we put it compared to B? Higher, right? Pretty straightforward. So we're saying A may have a choice. It's going to react to give B, or it can react and instead form D. Which pathway is it going to take?
The easiest.
The lower energy pathway, right? So B is going to be formed preferentially. And since B is formed preferentially, that's what BR then attacks. And which product do you end up with?
C.
You end up with the BR on the tertiary carbon because that's where the carbocation forms. Right? B is more stable than D. Primary. You have this labeled as B, right? That's a tertiary carbocation. Did I get that all right? In fact, on reaction according to diagram, that's what we looked at. Okay? You would be higher. Water doesn't run uphill if it can run another way, right? Right? So this is why you have Regio Selectivity, and the reaction goes to B, and then ultimately to what? C? All right? Let's predict products here. Product of the first reaction. HCl is the same as H3R in terms of reactivity. So obviously we're going to make a alkyl chloride. When you react an alkene with HX, you get an alkyl halide, right? All right. Product. Now, do we just have some product memorized, or do we work through it using our mechanistic thought? Your mechanistic thought is like an equation in math. You use that to get your product. What's the first step here? I'm not just going to throw out a product. I could, but I wouldn't expect you to, and I wouldn't want you to. What's the first step? Does an alkene attack H+? Polarized, yeah? Here's the question I will always ask. We're going to make a carbocation, yeah? Would you rather leave carbocation at top or bottom?
The bottom.
Top, because it would be tertiary. So the electrons are going to break away from top and go make bond to H. Pull them away, go make bond to H, and this needs to do that. What does that electron movement give? I'll draw in the new H. There's a methyl up there. And that up there is a carbocation, right? There's our carbocation intermediate. Next step. Plus what? What else was formed here? Chloride. All right, what's the next step? These electrons add to H, add to the carbocation, and there's your product. Is that what you would have predicted? Questions about that? I bet there's probably 50 questions, but we'll take one.
I was just confused. Can you please explain why we did the bottom one instead of the top one?
What do you mean? Well, we did
Why-
what bottom one?
Why
Where do
did
you want to
we-
leave cation, top or bottom?
Oh, the two bonds.
Do what?
Bonds.
Bottom? No, top. Top. Do you want to look at the bottom? If we had made carbocation on the bottom, what would it look like? If instead the electrons went up and made new bond up here to H, leave that as a cation, which is better, this cation or the one over there? This is secondary, and this is tertiary. Tertiary is better. So it's going to have a lower transition state leading to it. It's going to be the one that's formed. That's what we showed on the previous Regio Selectivity. Okay? CO minus attacks carbocation, we get product. Other questions? Just bring them on. Let's get them answered. Question?
So is that hydrogen still attached to that carbon
Sure
at
it
the
is.
bottom?
I just drew it in for clarity of what was added. Yeah, if you looked at that structure over there, I mean, other than my bond is not connected, but that's, if I try to connect it, then it's going to look skewed. See, now it looks like what happened here. If I showed you that on day one and said, how many H's are here? Two, right? Well, how many H's are there? Only one. There's a new one there. Yes, I would typically draw in the brand new H to illustrate that, hey, this was just added. But I won't keep doing it as we move forward. Otherwise, we'll end up with a structure with all H's drawn. This is not how you draw a structure. Next question. Question? Wow.
Had that top bond not been there, would it matter which way the carbon bond swings?
Top bond, which bond?
The one that's coming off of
The methyl?
the methyl, yeah, the methyl. If that wasn't there on the original,
It doesn't matter anyway, as long as you got a chlorine connected to that carbon.
oh, no, I know, but like, would it matter which way you swung the bond? Because either way, it wouldn't.
Good question. We'll see that coming up. That is, maybe there you have no reason for Regio selectivity. Is the reaction Regio selective?
Yes.
Yes. That is, what will be the Regio isomer? A possible Regio isomer here. Be this. That's where the new H is there. Everybody see the new H there? And the Cl is here. Again, do we add HCl like this? Across the double bond is what we say. Or do we add HCl like that? Well, Cl is going to be on top. Yes, it's going to be Regio selective. If the answer was no, the answer would only be no if you get these in a 50-50 mix. It's like no selectivity. The reaction is not going to give this. Why? Because the secondary carbocation is not as good as a tertiary. You're going to get this because you got that. Once you get this, then you can only get this. Yes. Next. Product down here.
You're gonna get the iron attached to the fourth carbon.
Is the iodine going to be on the end carbon or the second?
Second.
Yes. 1, 2, 3, 4, 5. Iodine here. There's your product. Okay? You can draw it under there, or you can put it over here, draw an arrow with it. Regio selective, yes. What's the first step in this mechanism? Alkene attacks H.
Okay.
Leave carbocation where? Right or left?
Left.
Left, secondary. Secondary is better than primary. And then I minus attacks secondary carbocation. Okay? Third one. Where are you going to make carbocations? Left or right? Left or right? In this case, either. Carbocation over here would be secondary, over there would also be secondary. Which one's going to be preferred? Neither. There's slight differences, but for us at this stage, the answer is neither is preferred. If neither is preferred, is it going to be selective for either product? No. So it's not going to be regio selective. So down here, you're going to get you'd actually get this product, okay, A. This gives A. This down here gives A, that product, plus what? It's also going to give iodine there.
So, question, doesn't matter which one we show, because I got the one on the right, doesn't matter if you give one on the right or A.
For the third reaction,
Is that?
you want to give them both. If you only give one, you're saying one's going to be preferred over the other. That's not the case. You need to understand that neither is preferred, and so you're going to say, hey, which is going to be a better reaction? A good reaction is the ones that typically give a single product that you can get a high yield of a single product. Which one's a better reaction?
The one about that, the one that gave A only.
Yeah. Let me ask you this. If you wanted to make A, would you make it from this alkene or this one?
First, second one.
It's pretty obvious, right? If you wanted to make A, you would start with this alkene. Okay? All right? So you go get a job and you go to, hey, we're going to make, our goal is to make an alkyl iodide. Tell me, young sir, young ma'am, how would you propose making it? All right? Don't propose this way. Propose this way. You'll get a better reaction. All right? Because it's the top, the above reaction is more regio selective. All right?
Would the second option be more favorable because of symmetry or something like that, the inductive pushing symmetry, versus A, the inductive pushing symmetry is not symmetrical?
No, that really doesn't matter. Both
Okay.
of them are secondary, and that's really all you. The secondaries are secondary until beyond that would be very fine argument that we're really not going to get into.
Understood.
Okay, so we're picking up terms. Yeah, we're introducing this. What's next? Synthesis. Okay. Synthesis is going backwards, and we kind of went backwards a little bit there, but here we go. Provide a high-yielding regio-selective synthesis of this. How would you make this compound? And as we go along, the synthesis will be important, and you develop your toolbox of reactions. And you learn, okay, how do you make alkyl bromides? Right now, you only know one way, and that's reaction of an alkene with HBr. By the end of organic 2, you may know half a dozen ways. All right? So, how are you going to make this? From an alkene, because that's all we've done, right? Which alkene? Would you rather make it from that alkene or that alkene?
Top one.
And by the way, we know alkene nomenclature. Okay? Need to be working on it. Which one of these is stereogenic?
This second
All
one.
right. So those are questions we need to be able to answer from the alkene nomenclature. I would react it from here. Where are you going to make cation here, left or right? Both, either. You're not going to be selective. You're going to get two different carbocations. Both will be secondary. How about here? Where are you going to make cation, left or right? Right. This is going to attack the H+. The electrons pull away from that carbon. Okay? Here. And that gives what? That gives that carbocation. And then how do we get final product?
The
BR.
BR.
I'm not going to show mechanistic. Arrow, right here is what I want to say before we end here. Look at that arrow right there. Which carbon is bonding to the H? Many of you will come to say, that carbon's bonding to it. Look, the arrow's right there. No, that carbon is not bonding to the H. What is happening here is, here's this. Somebody pull my wrist, okay? There's an H behind me. This goes over there. Here we go. Here's carbon and here's the other carbon. The H is behind me. Pull it. Okay? Which now is bonding to the H? That carbon over there? No.
The end.
We pulled the electrons away from that carbon. Pull them away. This swings like this. Here we go. Pull the pin. Now this is bonded over here. But see, you guys tend to think that that carbon's bonding to the H. You got to understand we're moving electrons. We're swinging them out like the barn door or the gate. Okay? If I swung this out, it's still connected over here. It's leaving there. This is how we move arrows. Okay? You can do the next one. Okay? And you can be looking ahead. Because I started a little slow at the beginning. Yes? As you move forward, we'll say the same things. We'll keep repeating the same things. We'll make the same assessments. And we'll see that everything, the commonalities. Okay? All right, guys, this is stepping it up a notch. All right? See some of you in lab this afternoon. Have a good day, guys.